Good afternoon. On behalf of Engineers Australia, I'm delighted to welcome you all to our Thought Leaders series, Underground Stormwater Storage for Detention or Reuse. My name is Amanda and I'll be your host for today. Firstly, in keeping with our custom, Engineers Australia acknowledges the traditional custodians of the country throughout Australia and recognises their continuing connection to land, waters and community. We pay our respects to them, their cultures, and to elders past, present and emerging. Before we get started, I'd like to acknowledge that today's webinar is being hosted with Engineers Australia's industry partner, ACO. ACO in Australia offers an extensive portfolio of stormwater, building drainage systems, cable pit and ducting systems, access covers and other niche products. The company has for just under 30 years been Australia's foremost manufacturer with facilities in Western Sydney, New South Wales. ACO takes pride in providing excellent customer service and extensive technical support from specification to the finished product installation. Today, we will hear from two speakers, followed by our live audience Q&A, and I encourage you to send questions through to our speakers via the YouTube chat box. We will also be inviting you to participate in a live poll and competition question during the Q&A. And now I'd like to welcome our first speaker, Mark Liebman. Mark is a founding director of Sustainability Workshop, developing a strong standing in the industry, and is a thought leader and innovator in the water and environment arena. Mark has more than 20 years' experience, which has seen him working on projects in the Republic of Georgia, China, UK, Japan and Australia. Over the last 20 years, Mark has helped to pioneer water-sensitive urban design in Australia, with specific fields of expertise in water quality, management, modelling and design of treatment trains. Please welcome Mark Liebman.
Thanks very much, Amanda, for that introduction. I begin today from my office in Blackheath in the Upper Blue Mountains by acknowledging the Darug and Gundungurra people, traditional custodians of the land on which we virtually meet today, and pay my respects to their elders past and present. I extend that respect to the Aboriginal and Torres Strait Islander peoples who are in the audience today. Welcome, everybody. Just a little bit about Sustainability Workshop. We are a small independent consultancy. I myself am a chartered civil and environmental engineer. I've got 25 years experience in the urban water management industry, and a key part of our work is designing disconnected stormwater systems and protecting our precious creeks and rivers. I wanted to give a brief overview of the presentation today. I begin by defining a pretty wicked problem called the urban stream syndrome. We talk about infiltration as one potential solution to that problem. Talk about the challenges and the limitations of infiltration. It's certainly not a practice that you can implement everywhere, but where you can implement it, it's a fantastic approach. We talk about how to model infiltration systems briefly, and then we look at a case study at Umina Beach. We also go through and review a number of projects which have informed the thinking behind the solution at Umina Beach. Towards the end of my presentation, we'll look at maintenance and discuss some of the critical issues. Following my presentation, there's a 3-minute short video on the Umina Beach project. This slide is showing one of the most visible impacts of urban stream syndrome, obviously gross pollutants, but by far it is the easiest aspect of urban stream syndrome to address. It is much harder to address the changes to hydrological regimes that result from sealing off the land and cutting down trees. Veets, Walsh and Fletcher have been researching in the space for a very long time, probably since 2004. They define urban stream syndrome as an almost universal physical and ecological response of streams to catchment urbanisation. It is not a phenomenon that's particular to Australia. It happens all around the world wherever you have urbanisation. It is what happens when you directly connect drainage systems via gutters and pits and pipes to natural waterways. This slide shows the hydrology of a natural forested land use at left. Most of the precipitation that falls on the forest returns as evapotranspiration. Some of that water infiltrates where it provides absolutely significant base flows, which sustain our creeks through dry periods. And you get a small amount of surface runoff that happens very infrequently. If you compare that to the urban water balance shown in the middle of the screen, you can see there are some pretty dramatic changes. Very little of the precipitation that falls is returned back to the sky through evapotranspiration because we simply cut down all the trees. You get a dramatic increase in the frequency and volume of surface runoff, and obviously the quality of that surface runoff is degraded quite dramatically. And it's also logical that if you seal the land, you stop infiltration. Using water-sensitive urban design, we have an opportunity to try and restore some of that water balance. We can see the changes in numerical terms in this slide. I took the opportunity to model a 1 hectare forested land use in the Hunter Valley, and that served as the pre-development scenario. I modeled what happens when you convert that forest into 1 hectare of industrial land use, which is completely sealed. The frequency of surface runoff changes from once every 2 years to 70 times per year. Mean annual runoff volume has a 10-fold increase, and the volume of evaporation reduces by 7 to 8-fold. We lose all of the water that goes into the ground as infiltration. This is another way of graphically depicting exactly what I've just described. It shows a runoff histogram for the pre-development forested land use on the left and the runoff histogram for the post-development urbanised land use on the right. I had a 40-year, 6-minute time step model. Pre-development, we've found that we generated 20 runoff events, but post-development, we generated 2,760 runoff events in 40 years. You can imagine the impact of this increase in the frequency of runoff on the macroinvertebrates that would inhabit the waterways downstream of this hypothetical development. Ladson, Walsh, Fletcher, Cornish and Horton have also been researching in the space. They've shown the correlation between stream health and total imperviousness. Imperviousness here is defined as the degree that impervious areas are directly connected to the receiving water. For example, a shed in your backyard which doesn't have any gutters or downpipes and which is surrounded by green lawn is said to be disconnected. However, your house roof or a building roof which has gutters and downpipes and which is directly connected to the receiving water is literally directly connected. What's disturbing about this chart is that it shows that even with a small increase in imperviousness, you see a decline in ecological condition. And that decline continues with increasing imperviousness. So what is the solution? The solution is simply to find ways to disconnect the stormwater and to restore some of the lost water balance. Mimicking pre-development hydrology is a really big ask, and I don't think that we have the technical knowledge to do that at the moment. We may at some point in the future. Rainwater harvesting and infiltration result in degrees of disconnection. Even small tanks and infiltration systems work really well to mitigate the impacts. Obviously, larger tanks and larger infiltration systems will work better, though there are diminishing returns. In the past, every plumber could install a rainwater tank and build an absorption trench. This was standard practice in many parts of Sydney. It still is in the upper mountains where I live, and this may explain why our creeks are still in pristine condition. The challenge of infiltration, and there are certainly lots of challenges and lots of limitations. It's not a practice that you can apply everywhere, but where you can, it works really well. Infiltration works really well in the short term. It can also work well in the long term if designed with effective pre-treatment, which is also maintained. Without pre-treatment, sediment can cause clogging of the infiltration system, and this will reduce the performance over time. Our case study focuses on pre-treatment, and it demonstrates the importance of pre-treatment. High groundwater can also influence the rate of exfiltration and limit the opportunity for infiltration. We did encounter high groundwater in our case study. Bedrock is frequently a challenge. However, it doesn't necessarily mean that it's a showstopper. I come across plenty of sites in the upper mountains where the bottom of our infiltration systems is located on bedrock. However, there is ample opportunity for water to seep out the sides and still perform really well. Heavy clay soils, such as the kind of soils that you get in Blacktown and the north and southwest growth areas of Sydney, are really not great for infiltration. Their hydraulic conductivity rates are simply too low, and water sits in the trench without draining away. Saline and sodic soils can also pose very serious challenges, and it is currently recommended to avoid infiltrating on saline soils. I would also be very careful about infiltrating on reactive shrink swell soils, especially if you're proposing a trench in close proximity to a building where there is a strong risk of cracking. Australian Runoff Quality recommends minimum separation between an infiltration system and a building when on clays of 4 metres, which can be reduced to 2 metres when you're on sand. I just wanted to share an absolutely excellent design reference. This is the WSUD Basic Procedures for Source Control of Stormwater, edited by John Argue and including other authors like David Pizzaniti. It includes a wealth of research by John that summarises his findings over pretty much a lifetime of researching permeable pavements and infiltration solutions. You can grab a student edition of this document on the web. So how can we model infiltration systems? Look, we can use music, which is a continuous simulation model. It's great for working out infiltration volumes and particularly good for helping you understand how frequently those systems are going to fill with water and spill. I also use drain software by Watercom. Actually, I typically use both softwares to check my designs because most designs are done to a specific design storm recurrence interval, for example, 1 in 3 month storm event or 1 in 5 year event. But you also need to know how these systems are going to perform on a daily basis. Recent updates to drains make it much more flexible in the way that it models infiltration systems. The critical parameter for both models is having a good understanding of the long-term saturated hydraulic conductivity. So John Argue has suggested adopting 20% of the measured field rate, and that is without pre-treatment. My recommendation is that you can increase that to 50% on the basis of having good quality pre-treatment. So now we move on to the case study at Umina Beach. This project is located on the central coast of New South Wales. Central Coast Council were lucky enough to get a pretty sizable grant to construct a regional state-of-the-art skate park and pump track and sports facilities. The project site you can see is the disturbed area in the centre of the slide where the skate park and pump track are currently under construction. Heading towards the beach, you can see Sydney Avenue, which has recently been reconstructed. And between the skate park and Sydney Avenue, you can see a brand new footpath. And further north is the infiltration system. You can see the back dune below Sydney Avenue, and you can see Umina Beach very close to the site. This slide just provides a bit more context, and it's looking south. You can see the back dune to your left. The back dune rises up about 3 or 4 metres above Sydney Avenue. The park is to the right. The infiltration system is located approximately where that basketball court can be seen. The problem that Central Coast Council were dealing with at Umina Beach was really challenging. As you can see, they were dealing with extremely flat grades, poor piped infrastructure, and water ponding for prolonged periods of time in the car park, causing nuisance flooding to residents. There was also absolutely no discharge opportunity. We couldn't discharge to the ocean. An ocean outfall would have absolutely been knocked on the head. And we had no other piped infrastructure to connect into. Infiltration was the only option. It's also worth noting that this is in the context of Central Coast Council encountering a number of failed first-generation infiltration systems elsewhere in the LGA. They failed because Council couldn't get access to those systems to clean them out. So Council commissioned Douglas and Partners to carry out a geotechnical investigation, and this was undertaken in 2 stages. The first stage investigated the area circled in red and unfortunately returned some pretty poor results. We had low infiltration rates and elevated groundwater. We then commissioned a second investigation, which is the area circled in green. We got much better infiltration rates, really very high in fact, and no groundwater was detected. In the end, we adopted a conservative design infiltration rate of 100 mils an hour, which was actually well below the in situ test results. So the solution at Umina involved bringing together 2 infiltration systems. The first system is the hydrocon permeable concrete pipes, and the second system is the ACO Stormbricks Geocellular stormwater management system. So hydrocon permeable pipes are a water quality treatment device. They provide the pre-treatment to preserve the life of the geocellular system. They are made from permeable, no fines concrete. Water passes through the pipe walls and into the gravel surround. Research undertaken in Germany has measured the exfiltration rates of those pipes under different head conditions. The pipes play a critical role. They retain the majority of the sediment within the pipe while allowing water to permeate through the pipe walls. They're very easy to maintain. ACO Stormbricks provide cost-effective underground storage. They have a porosity of over 95%. They're also backed by research undertaken by Syria and the UK, where use of infiltration for flood mitigation is mainstream. They have been designed to consider a creep failure mechanism for repeated loading, and they provide access for maintenance. The design solution at Umina was to place a 500 ml hydrocon pipe inside a gravel trench and to have 2 rows to have 2 rows of storm bricks each side of the gravel trench. Water comes into the concrete pipe from the road, it passes through the pipe walls while the sediment is retained inside the pipes. The water seeps into the gravel trench and then into the storm bricks. Water can seep out of the hydrocon pipe at a much higher rate than it can infiltrate into the ground. Therefore, water would build up inside the trench and be stored inside the storm bricks. Water would continue to infiltrate until the end of the storm event. There's a major system overflow whereby high flows are allowed to flow through the hydrocon pipe system and into the parkland beyond. I wanted to briefly review a number of projects that have helped inform the thinking and informed a lot of research and knowledge gained using these different products over time. The first project is located at Kiama in a well-used public park next to Black Beach. The system uses hydrocon pipes located within a grassed storage basin. Under low flow conditions, water flows into the pipes and seeps out into the surrounding sand media. Under high flow conditions, water surcharges up out of those pits and it ponds in the basin where it can flow vertically down through the sand media and be treated before being discharged. Another project that we applied the same thinking on is the Ashgrove Estate in Regents Park. Here we treat stormwater initially in a gross pollutant trap. The water then flows into hydrocon pipes where we settle out any remaining sediment. From there, under low flow conditions, water seeps through the walls of the pipe, and under high flow conditions, it reports to the surface inside a detention basin. This detention basin is used for both water quality and flood mitigation purposes. Most of the time, the basin is a valuable public open space resource and it's very well drained. A key take-home message here is that space in Sydney is at an absolute premium and that we don't need to sacrifice public open space by sterilising that space with a stormwater treatment system. A similar approach has been adopted by Blacktown Council for their bioretention basins, where permeable pipes are used to trap any sediment that passes through the upstream gross pollutant traps. In this context, the permeable pipes are designed to protect the filter media and to ensure that filter media, constructed in large part using very precious virgin natural sand resources, lasts as long as possible. It would be incredibly challenging for council to replace all of the filter media, and it would cost many millions of dollars, and they simply can't afford to do it. I've also undertaken hundreds of smaller and larger infiltration projects in the Blue Mountains over the last 10 years. Absorption is a deemed to comply solution under the council's DCP. Using ACO storm bricks is a much more cost-effective solution than a traditional trench, which is filled with gravel and only 33% porous. That means only 1/3 of the volume of that trench is available to store water. You can compare that to the storm bricks, where 95% of the volume is available to store water. It means a much smaller footprint, less excavation of natural soils, and less waste management. I wanted to talk briefly about maintenance, which is absolutely critical. It's really important to understand that if you can't maintain a system, then it is going to fail. That's a given. The first generation in systems installed at on the Central Coast lasted between 5 and 10 years before failing. I understand this to be more or less in line with John Ige's research. All of the approaches shown today have maintainability built in from the start. Ensuring access for maintenance vehicles is critical. They need to get in close to be able to maintain these systems at a cost-effective price. The pipes are maintained by a ducted truck which used a high-pressure jet to push sediment toward an inlet pit where a vacuum hose removes the sediment and any other debris. The pipes are really easy to maintain, and it would take about an hour to maintain a 20 to 40 metre length of pipe. If you need to maintain the ACO storm bricks, you can also do that, as you can see in the image at bottom right. Thank you very much. I hope you got something out of that presentation, and following from this presentation is a short 3-minute video. Thank you, everybody.
Central Coast Council recently redeveloped an existing ageing skate park. Due to regular flooding, this required the existing car park to undergo major stormwater remediation. According to a council representative, surface stormwater runoff on Sydney Avenue originally flowed to a trapped low point, which consisted of a single pit with small PVC pipe outlets that regularly became clogged and took several days to drain to the adjacent reserve.
So the whole purpose of this project was to get rid of the water away from the car park and put it underground, so it can naturally go into the subsurface.
The site was heavily constrained by the existing stormwater network, insufficient pavement falls, its surrounding topography, and the environmental restrictions placed on ocean outflows. A solution would need to overcome these factors and function with the area's high annual precipitation and worsening summer storms.
For this project, there were various drainage constraints, so treating stormwater at the source was the only feasible option, as opposed to treating water at the end of pipe. Adding to the downstream stormwater infrastructure was simply not an option, except through an overflow pipe.
As the sandy soils in Umina enable high infiltration rates, Central Coast Council sought to integrate an underground infiltration tank with an upstream treatment device. Adjacent to the existing concrete footpath running alongside Sydney Avenue, Hydrocon permeable concrete pipes were installed between two twin ACO Stormbricks tanks of a total of 63 metres. The system needed to store the stormwater volume of a 1 in 5 year storm event.
This was a really unique project because it gave us the opportunity to bring together two great products, the ACO Stormbricks and the Hydrocon pipes.
Whilst these products are often used independently, this project is the first in Australia, bringing two manufacturers together to create an intelligent solution. ACO Stormbricks is a unique plastic geocellular stormwater management system designed for surface water storage and infiltration, retention, and detention for light and heavy-duty applications. Strong and quick to assemble, the Stormbricks tank offers optimum storage capacity with a 95% void ratio of total volume.
The ACO Stormbricks provides a very affordable means of underground storage, and the ACO Stormbricks have also been really extensively developed in terms of their structural integrity, unlike some of the first generation plastic products.
According to the builder, the installation of the Stormbricks tank was relatively simple. Once the trench floor was excavated and levelled, assembly of the plastic units was quick, with no real handling issues. They were very impressed with the system, ease of handling, how they locked together, the red clips that tied in the bottom and top levels, and the strength of the units once assembled.
Hydrocon has been in Australia for over 20 years and specialises in permeable concrete pipes and pavers that are used for water-sensitive urban design. Hydrocon permeable concrete pipes remove and retain stormwater pollutants within the pipes. Treated water exfiltrates through the walls of the pipes and is delivered to the subsurface of bioretention and stormwater filter systems. This prevents clogging and allows easy maintenance. This also reduces the life cycle cost significantly. Our products reduce runoff, local flooding, and improve water quality. Stormwater treated by Hydrocon products can then be harvested for reuse or infiltrated directly into the ground.
Stormwater is collected from the roadway and directed to the Hydrocon pipe system. The stormwater is then treated as it exfiltrates through the permeable structure of the Hydrocon pipes and into the gravel surrounding it. The water then enters into the geotextile wrapped Stormbricks tanks for temporary storage. During a storm event, the water table surrounding the tank rises. The tank allows excess water to be stored until the water table begins to drop, following the storm event. The stored stormwater then exfiltrates through the geotextile wrap and drains naturally into the earth and water table beneath. Stormwater pollutants are retained inside the hydrocon pipes for removal during periodic maintenance. The infiltrated water through the soil has the added benefit of replenishing the local groundwater close to the tanks. Hydrocon pipes have a flat base that allow them to be easily positioned and quickly installed. They connect into each other and are laid at a zero gradient.
At ACO, we are always ready to support customers with any design questions they may have. Initial communication with Central Coast Council was to provide information about the Stormbrix HD tank, the footprint, tank size, what volume, what they needed from our product to achieve that sort of volumes, and how it can be integrated with the hydrocon pipe. We provided a bill of materials, a structural calculator based on Series 6800 to make sure the tank was going to be functional and performing to load requirements. Finally, a detailed tank installation drawing was provided to show the tank layout and location of the access points.
The ACO Stormbrix and Hydrocon system offers easy maintenance and inspection throughout its design life.
So hydrocon pipes, they let water go through and they keep all the sediment and gross pollutants on the inside of the pipe where they can be vacuumed out of it. So they work as a really high quality filtration device. And what it does is it reduces the maintenance burden on the ACO Stormbrix, and we can extend the maintenance period on the Stormbrix right out. First generation systems were completely closed up and you couldn't get inside them to work out how much sediment was in them or even in fact remove the sediment if they were full of sediment. The second generation systems, like the ACO Stormbrix, are open, they're accessible, you can get CCTV inside them, which makes life very easy for the guys that are going to do the maintenance. They simply drop a vacuum hose down it and a high pressure jet, and they push all the pollution to one side and then vacuum it out of one of those pits.
This system provides Central Coast Council with an easy to maintain and cost-effective infiltration system.
Thank you, Mark, for a great presentation. I'd now like to welcome our second and final speaker, Darren Chan. Darren is the brand manager at ACO for civil construction products and the authorised representative for ACO's testing laboratory at the National Association of Testing Authorities, Australia. At ACO, Darren continues to support engineers and designers with innovative products and free online design tools. Please welcome Darren Chan.
Hi everyone, and welcome to our presentation on Geocellular stormwater tanks. Before I start, I want to thank Amanda and the EA team for their help in making today's webinar possible, and to Mark for an excellent presentation. Over the next 25 minutes or so, I'm going to describe the role of these plastic tanks, their characteristics, and offer you a guide on how to specify them. Underground tanks are used in lots of projects as councils legislate to protect their downstream waterways and infrastructure. Managing both the quantity and quality of water being discharged off a site is only going to grow in importance, particularly as our cities urbanise and rainfall events intensify as the climate changes. These days, larger areas of the built environment are being covered by impermeable surfaces, which of course increases the risk of flooding. Tank solutions are a conventional way to store and slow down the surface runoff to pre-developmental rates, as well as replenish the groundwater at a more natural rate. These are the system elements that are designed to work with the natural water cycle. On a slab or pavement, drains are typically positioned to intercept or collect stormwater runoff, which is then treated or cleaned to prevent clogging or contamination downstream. As you can see on the image, there are a number of tank solutions available to engineers and urban designers, both natural or engineered structures. Some of the engineered tank solutions include cast-in-place, precast concrete tanks, arches, and plastic structures. We'll focus today on just plastic stormwater tanks, which can be easily integrated in a stormwater management plan for the infiltration, retention, or detention of surface water runoff. Detention systems, also known as attenuation systems, are designed to spread the peak flow of a storm event. It does this by holding and releasing stormwater slowly. As I mentioned before, the idea of this is by controlling the runoff to reduce the risk of flooding downstream from a development. A retention system collects and stores water permanently for reuse, for example, to water landscape areas or for firefighting purposes. Infiltration systems, or soak wells, are used a lot in sandy areas to temporarily store water, to allow it to naturally seep back into the ground to replenish a dropping water table. To illustrate this, retention and infiltration are two common adaptations of these tanks to make the best use of captured stormwater. Retention is for irrigation or reuse purposes. Infiltration is where the soil can naturally free the water from impurities. In both cases, the water is used at or close to the source of collection without it flowing through to any downstream infrastructure or receiving waterways. But if discharging into downstream infrastructure is the objective, then as I explained before, detention gives designers the greatest control over the quantity of water to enter it. In very simple terms, it's an easy calculation. Before I go on, I want to make special mention on two types of hydraulic control structures. First are stormwater treatment devices. These are located upstream of the tank, with their performance being individually assessed and governed by the EPA and local DA requirements. And depending on the project requirements, there are many types from gross pollutant or silt traps, stormwater filters, permeable pipes, to even light oil separators used where hydrocarbons exist. The other type of hydraulic structure are flow control devices, which, as the name suggests, control the release of water to prescribed rates downstream of the tank. These are typically installed in chambers with either purpose-designed mechanisms or just a conventional orifice plate. Now, both these hydraulic control structures are not the topic of today's presentation, but I wanted to mention them as they are essential elements that affect the quality and quantity of water being discharged off the site. I want to go back to this slide to give an overview of the storage options available. From the top, we've got a detention basin. You often see these used in low to medium density areas. They tend to take up space that could otherwise be used for urban or commercial development. Then next are concrete tanks, normally expensive to construct and transport. Next along are the plastic arch systems, which require a decent amount of space. And finally, plastic tanks, and within this large category, there's a huge range of options, with not all being equal. So today, I'm going to focus on plastic tanks that can be assembled into producing underground cells for water storage. These can be adapted in a softscape where infiltration can be achieved. Here you can see them assembled, wrapped, and backfilled. They can be installed under slabs in commercial and industrial applications where space is a premium. This is an example of a tank being used for detention in Griffith, New South Wales. Designers had to deal with runoff from the site. The tank would store and gradually release the stormwater runoff into the council's downstream infrastructure, while also allowing direct access for watering the sports fields. In the industry, there is a wide range of plastic tanks. The two on the right are typical of plastic crates. The one on the left is typical of a modern geocellular unit. Unlike concrete tanks, plastic tanks are versatile. They can be cut and joined, and the structure can be used for infiltration. Good designs have a high void ratio and are easily maintained. Good designs are also load rated and hold their strength over time. But there are poorly designed plastic tanks that are difficult to access, inspect, and maintain. Unfortunately, these give all plastic tanks a bad name. Finally, the designer must ensure these products are integrated and meet the quality and durability requirements of the stormwater management plan. So, when specifying plastic tanks, there are a number of things to consider. Councils, through their development control plan, will enforce compliance to regulations. They will specify the methods an engineer needs to use to ensure the property meets the stormwater management plan. This takes into account the volume of water that the property needs to manage from landscaped, hardstand, and roofed areas. Not only does the certifying engineer need to integrate the tanks properly, but as with all key stormwater products, the structures themselves need to meet minimum strength, durability, and quality requirements. In Australia, there are no standards that govern plastic tank systems. And the problem with that is that some manufacturers make claims about strength and design life that just aren't substantiated. However, there is a UK standard for plastic tanks called Structural Design of Modular Geocellular Tanks. It gives guidance on testing, structural design, construction, and installation. This is the gold standard to benchmark performance, and as such, manufacturers should qualify their products to this standard to ensure that failures don't occur. A structural design should consider the load-bearing capacity of the tank. The stronger the tank, the shallower it can be buried, resulting in reduced construction costs. What determines the depth of cover required are things like the soil type, tank design capacity, groundwater level, pavement thickness, and design loads. The UK standard identifies these being the main factors overlooked that contribute to failures. And manufacturers must be able to come clean on their strength data and prove it with independent testing. To address all this, the UK standard has detailed all the requirements for laboratory strength testing. And when considering loads, both short-term and long-term loads must be addressed. Dead loads include the mass of soil surrounding the structure, plus the weight of slabs or anything else permanent that a tank will be subjected to. Live loads are temporary loads like vehicles, which also need to be considered. Tanks that have vertically aligned load-bearing pillars will offer good vertical strength and stability, and manufacturers should be able to provide you with independently tested vertical load results. Lateral loading is as important as vertical loading and takes into consideration soil mechanics. This is the key driver to how deep a tank can be installed. Be aware that specifically in high water table applications, tanks can be pushed out of the ground. So in these instances, either locate the tank close to the surface to avoid the water table or beneath a heavy pavement to anchor it down. Great emphasis should be placed on jointing methods. Systems that use a combination of brick bonding and cross bonding allow for a more rigid tank construction. Again, manufacturers should provide independently tested and certified lateral load data. This is to justify the installation depths they recommend for your project. Some manufacturers have a tendency to only disclose the short-term and not the long-term results of their tanks. Products need to be able to sustainably support loads over the design life of the project. This is crucial for a durable installation. Tank materials are liable to creep, meaning that they deform over time, and products must be strong enough to withstand this. The long-term strength test data allow manufacturers to determine the design life of their tanks. Not appreciating long-term strength can have extreme consequences. This is an example of an installation where the tank has failed because of creep. It's really everyone's nightmare and just highlights the importance of long-term strength. Here's another, not a sinkhole, but an actual tank failure in Pittsburgh, Pennsylvania. Taking a tank out of a controlled environment like a laboratory and measuring behaviour in a typical environment gives all stakeholders a better indication of performance. Whilst the UK standard provides methodology behind laboratory static tests, ACO conducted a full-scale live load test on a buried tank to an American standard. This was documented by Ohio University, equipped with sensors to measure vertical deflection and lateral movement, the tank was installed as it would be in practice. Here is a short video of the test. This video and the test report is available on ACO's website. As there are no Australian standards governing the strength of plastic underground stormwater tank systems, we've teamed up with Engineers Australia to detail everything you need to know on the topic. This is so you can integrate tanks into a project properly without the risk of tank failures from either short-term dynamic or long-term dead loads. If the web address on the screen is too long for you to write down, it'll be sent to you after the webinar. For tanks, the hydraulic capacity refers directly to the volume of water that the structure can store, and different tanks in the industry will of course offer different capacities. You can optimize the capacity of the tank by selecting products with high void ratios, which is over 90% for geocellular systems. Having such a high void ratio reduces excavation and obviously the construction costs because of that. Now, arch systems, just for a quick comparison with geocellular systems, have a void ratio of around 50%, which essentially means the excavation needs to be almost twice the size. Arches hold water in the open space beneath them, as well as in the voids between the stones. This isn't an efficient way to hold water, not to mention the additional cost of the stone fill. On the screen is an example of two tanks side by side offering the same storage, and you can see the installation volume of the geocellular tank on the right is considerably smaller. Let's look at concrete structures. Although concrete tanks provide 100% water storage inside the tank, they do have thick walls which reduces the void ratio to around 80%, and they are expensive to build and install. In comparison, geocellular tanks are more economical while still providing a high amount of storage. For concrete pipes, they're obviously round, but need a square trench. Each pipe needs about 250 millimeters of sand or stone bedding and around half a meter of spacing between each run. All of this increases the excavation and fill required, making the installation bigger and more expensive. A good manufacturer should be able to help you optimize the space to meet the site's storage volume requirements. A tank versatile enough to shape itself around your project will give you more options to meet a site's storage requirements. Modular tanks offer the ability to adapt themselves to an underground shape with some level of flexibility. This is particularly useful when avoiding things like existing services, buildings, or footings. Manufacturers should give you tank layouts to help you navigate the physical constraints of your project, as well as clear installation instructions. As I mentioned earlier, tanks can perform any or a combination of these roles, and depending on how a tank is used, it requires a different type of wrapping. In non-sensitive retention or detention applications, geomembranes are used as the bladder for storing water with a geotextile on the outside to protect it. Now, as long as minor leakages from the tank can be tolerated, the membrane is normally just taped together. This is used in the vast majority of applications. But for sensitive applications, like a tank positioned close to a building or to simply contain contaminated runoff, we'd recommend using a welded geomembrane installed by an accredited contractor. This ensures water tightness, but as before, the geotextile wrapping on the outside needs only tape to secure it. The focus is on the integrity of the membrane. And for infiltration systems, there's no impermeable geomembrane used, just a geotextile which acts to minimize the sediment buildup within the tank while allowing for the water to percolate. Stormwater tanks can be very large, and moving them to site and then into the excavation can be costly. Geocellular plastic tanks are lightweight to transport, and the modules are designed to stack inside one another, which means they take up significantly less space than other products. This leads to fewer truck to site and fewer trips to the excavation. Not only is this more cost effective, but better for the environment. The site itself should be considered when selecting a product. The time it takes to store and assemble these tanks can significantly affect construction costs. Some tanks need storage, and worse still, some tanks simply don't stack. Some plastic crate systems are generally assembled away from the excavation, then lowered in. There are additional rent and labour costs associated with building and storing the tanks before installation. Geocellular stackable tanks, however, are really beneficial for sites with restricted space or labour, in that they can be built inside the excavation. So, to get access to a tank, a dedicated entry point for both inspection and cleaning is needed, like the inspection chamber shown on the top right. For inspection and maintenance, open cellular tanks provide uninterrupted access from one cell to the next. This is in stark contrast to the closed-in structures of traditional crate systems. A tank that can't be maintained serves no purpose. Cameras and jets must be allowed to pass throughout without restriction. Here is a short video of an inspection carried out in a modern geocellular tank design. A geocellular tank is located under a pedestrian precinct. A maintenance team has lowered a camera down a shaft through the inspection opening. You can see the camera move through the system easily without being restricted by any physical barriers in the tank. At the bottom right, you'll notice a chainage counter showing the distance travelled by the camera cable from the manhole. If I showed you the full video, the camera ends up 30 metres into the tank. This would not be at all possible in tanks constructed of plastic crates. And so, we've now come to the end of our presentation, but to summarise, these are the key things to consider when specifying tanks: compliance and legislation, the tank's design and strength, the void ratios for storage, how easy it is to transport, and the ease of access, inspection and maintenance. This now ends the formal of our CPD. A little bit about ACCO. These are our products for external applications. We offer trench drains designed for buildings, urban and civil infrastructure projects. ACCO Access is our range of access covers, and ACCO CableMate is our range of cable pits. Our own Geocellular tank is called Stormbricks. We have two versions, SD for vehicles up to 9 tonnes and HD up to 30 tonnes. Details of this product range can be found on our website. These systems can be incorporated into water-sensitive urban designs using the Storm Updated program by Clean Stormwater or Music program by eWater. To help you manage surface water for your projects, whether it be to collect, clean, hold or reuse it, I'd like to say that we're happy to help you across the board with all of our products. askacco.com.au is where you can find all of our pre-project services. These are designed to complement your own project-specific calculations. You can email us your project requirements or even ask a simple question to askacco@acoaus.com.au. Part of our suite of services is that we can help you with storage above ground or below ground. Where the consequences of ponding water on the surface are low, we can provide a ponding analysis where temporary ponding can be tolerated. We do this by deliberately undersizing trench drains to restrict flow. Alternatively, we can help you remove water entirely off the surface with adequately sized surface and subsurface drains. We have a technical team of engineers ready to assist you. For your specific projects, this involves us configuring both trench drains and tanks and providing you with a part schedule for that configuration. We can also provide structural tank calculations based on the UK standard structural design of modular geocellular tanks. We can provide you with a fully documented proposal specific to your project. This is a service offered free of charge and without obligation. To help you specify the correct size tank, we've designed a simple online configurator. All you need to do is to provide some basic information relating to your desired tank size or storage volume, and the calculator does the rest. The following is a demonstration of the new Stormbricks configurator program. Let's get started. To use the Stormbricks configurator, begin by registering or logging into the program. Then start a new project by entering the project name. All registered users will have their project saved. Saved projects can be accessed at a later date for review and revision. Choose the function of the tank, either detention, retention or infiltration, and select the Stormbricks system. You can configure the tank in two ways. Firstly, by specifying the tank dimensions by entering your preferred length, width and depth. The program will configure the tank to be within your preferred dimensions. Or secondly, by specifying the storage volume required. The program will configure the available tank layer and depth options for you to select. Next, you enter the cover required over the tank and the program will calculate the excavation volume and also calculate the volume of backfill required. The program is limited to a maximum of 3 inlet connections. And limited to 1 outlet connection. Then you can roughly position the access chamber locations and any additional access points. Select your preferred access covers And finally, add pipe connectors for ventilation and overflow if required. At the end, press the green Get Results button for a downloadable results page containing your inputs, tank size, storage volume, and a bill of materials. A product data sheet of the Stormbricks product is also attached. As you can see, a tank can be configured within a few minutes using the new online Stormbricks configurator program. To make the structural validations process easier, we've also designed a simple online structural calculator. It's very simple to use, and the required inputs include cover depths, height of water table, live loads, pavement type, and soil type. The results can be downloaded as a 2-page summary or a 6-page comprehensive report. The Stormbricks configurator and Stormbricks structural calculator are both available on ACCO's website for you to use any time of the day. If you would like to talk to us directly, we have technical representatives across the country who would be only too happy to assist you with your next project. Thank you so much for your attention today. I'll make sure our post-webinar email to you contains all the links necessary for you to learn more or simply reach out to us when you need to. I'll now hand you back to Amanda.
Thank you, Mark and Darren, for great presentations. Before we get started, I'd like to announce that ACCO will be offering a prize to the best answer of the following question. In less than 100 words, where do you see the future of underground stormwater storage? Great question. Please share your answer to the email address in the description box, and the winner will be announced in ACCO's LinkedIn page. We will now be starting our Q&A session and polling, and please ask our speakers your question via the YouTube chat box and who your question is directed to. Kicking off with the polling question and using the link in the description box to participate, each question will come up one at a time for you to answer. So good luck. Thank you to everyone, as always, who submitted questions whilst registering, and we might start with some of those. Darren, a question from Robert, and Robert is watching in Queensland. Good afternoon to you, Robert. Asking you, Darren, what issues arise with maintenance of tanks, methods, costs? Thanks, Darren.
Thanks, Robert, for your question. With the maintenance of tanks, it really depends on what kind of tank is installed. There are a lot of different types of tanks. When you're looking at concrete tanks are large, and you can get inside them to inspect them. But with that, you need to have confined space permits, and you also got to test for the carbon dioxide within. So, going into a dangerous confined space is not the greatest thing to do, but that's what can be done with concrete tanks. And then if we look at, as Mark mentioned in his presentation, the first generation tanks, the plastic tanks, those plastic tanks were like the crate tanks. You really couldn't get inside them, you couldn't clean them, so they'll just silt up very quickly, and they're just not maintainable. So with ACCO, we weren't the first ones to design these plastic tanks. What we did was learn from those kind of tanks, and we designed tanks that were accessible and maintainable. So with ACCO Stormbricks, we designed a pillar system where you can get access to within the tank through an inspection opening from the surface and a shaft, and then you can lower down CCTV into there to inspect the tank, and if you find that it is silting up, you can just get a vacuum pump in there and then suck up all the silt and remove it. So, with Stormbricks tank, it is accessible and easily maintained.
Thanks, Darren. And staying in Queensland, we've had a question for you, Mark, and also Darren, if you'd like to comment, from Nigel. Mark asking you, how can we design to clean them out easily?
Thanks, Amanda. I presume that the question is referring to tanks and how can we design tanks to clean them out easily. Obviously, you need to create as much access as you possibly can. But I guess from my perspective as a designer, it's more critical to make sure that you prevent sediment from getting in there in the first place. Excuse me, I would put something like a gross pollutant trap or a hydrocon permeable pipe, some kind of filtration device upstream of that tank to avoid having to clean it out in the first place. Darren, any thoughts?
Yeah, I totally agree with that. It comes in regards to in your early planning. Your cleaning product before the water entering the tank is the most important to clean the effluent that's going in and to take out all the rubbish and the sediments before it goes into your tank would lessen the frequency of cleaning your tank. Tanks can come in all different sizes too. Small tanks, you might need one access point because you can easily get around and to all parts of the tanks. But if you've got really large tanks, you're going to have really big tanks in commercial and industrial applications in big buildings where they might be 50 metres, 100 metres long. Then you need to strategically design where you're going to put your access points. Thinking about what is the restrictions with how you're going to clean it. So certain CCTV might have a certain range that it can go through the tank. So you might want to space your inspection points accordingly. And also you've got to think about if you're using pump trucks, what their range is too. So just careful planning in the design stage, strategically putting in where your access points are, either at each corner of the tank if it's a large tank, or at certain intervals along the tank. And then, definitely as Mark said, your cleaning product at the start definitely needs to be carefully designed and installed.
Thanks for that, Darren. We've had a great question that's come in from Simon in WA for you, Mark. Simon is asking you, Mark, does this technology have applications in regional areas? Mark.
Yeah, hi, Simon. Really good question. So I had the pleasure of visiting Perth a few months ago and learning about the type of systems that you use over in WA. Obviously, infiltration is more or less business as usual. I do understand that you have soils where you do regions where you get elevated groundwater. That is a constraint and a limiting factor. I would say both of the products that we've seen today, hydrocon pipes and ACO storm bricks, would make a fabulous combination for use in WA. I think from what I remember, your soils have infiltration rates approaching 300 millimetres an hour, which is fantastic for infiltration. In terms of sourcing your potable water from groundwater, I know WA does do that, and therefore I would pay a lot of attention to maintaining the quality of water that you use to replenish your groundwater with. Again, that combination would pre-treat that stormwater, I think, to a pretty high standard and protect your groundwater sustainably for a long time. Thank you.
Thank you, Mark. Mark, just staying with you for now, we've had a question from Jeffrey in Queensland who's asking you and then Darren. Mark, how do we address groundwater effects caused by an online detention absorption system? Mark.
Thanks, Amanda. And thanks for a really great question, Jeffrey. It's a challenging question to answer, and I think I have to interpret the question as asking, is it possible for infiltration systems to cause mounding or raising of the groundwater underneath the systems? And the answer is yes, it can, and it is definitely something that you need to be conscious of. Look, I'm guessing the soils where that could happen would be confined surface aquifers, sandy soils, and I would try to get along the longest possible record of bore levels, groundwater levels that you possibly can. I know that's difficult. You need to be well above your seasonally high groundwater table to make sure that the bottom of your tank remains above the groundwater and available to exfiltrate. Alternatively, you can be conservative in your design assumptions, assume the bottom of the tank is effectively sealed because you may have elevated groundwater, and then you can just model the impact of what comes out of the side of that system. I hope that answers your question.
Oh, thank you, Mark. Thank you. Darren, do you want to comment?
Yeah, with groundwater, especially when we're talking about Stormbrix tanks. Stormbrix tanks are plastic tanks, so if the groundwater is high above the bottom of the Stormbrix tank, it'll cause buoyancy pressures, uplift pressures onto the tank. And what if the groundwater starts rising up and the actual tank inside is empty? You'll get the effect of that groundwater pressure trying to pop the tank out of the ground through the buoyancy. So in these cases, you probably want to install the Stormbrix as shallow as possible to get away from that groundwater. Otherwise, install a very heavy pavement to counter that buoyancy effect and hold the tank down. So there is a consideration for that, and we have developed a structural calculator that takes into that consideration. So if you use that structural calculator, there will be a question on where the water table is in relation to the tank, and then those forces will be considered in our results that we provide.
Thanks, Darren. And just staying with you, Darren, for the moment, we've had a great question come in from Manuel, who's watching from New South Wales, asking, Darren, what products can you offer to mitigate flooding? Thanks, Darren. Thanks,
Manuel, for your question. Look, when we're talking about flooding, if you're talking about widespread flooding, there's not much you can do. That's more about dam levels and designing, not building in floodplains and all those kind of things. But when you're looking at smaller structures, detention tanks, these are all there designed to stop flash flooding, where just a short, intense storm where you're going to get a lot of rain in a short period of time. What we want to prevent is flash flooding downstream. So using on-site stormwater detention is what is used to stop to control the flow of the water off the site. Then hopefully you're not flooding the downstream pipes and stormwater pits and pipes downstream from that catchment. It's your development control plans in your local councils will have all the set outs of what you can do, what you have to calculate to allow the pre-development flow rates off the site. So your detention system must comply to that. So most of the time, your DAs will have an OSD component in it, and that's what you have to design to.
Thanks for that, Darren. Mark, we've had a question from Nathan asking you, Mark, if the soil is already saturated, what is the efficiency of these infiltration systems? Thank you, Mark.
Yeah, thanks, Nathan. That's it's a very astute question, and it's not easy to answer this question. I have been thinking about it since I saw the question come in. And I think it's all about understanding the context. So if you're in an urbanized scenario where, let's just call it an industrial estate, and you're effectively sealing off 85%, 90% of the ground, the probability of reaching soil saturation is actually pretty low. So that's the highly urbanized context. So yeah, I don't think that's likely to happen. Also, to reiterate what Darren has said there, you're principally trying to deal with, flash flooding, which, is a flashy response to an urbanised, impervious, directly connected catchment. So you're looking at the short term, probably the rising limb of a hydrograph, whereas soil saturation tends to happen after quite a few days of rainfall. The other context where this question is really a good question is, for example, where I live in the Blue Mountains, where we design a lot of infiltration systems. And I guess, we do get saturated soils, and certainly the last 3 years of rain has demonstrated that we absolutely get saturated soils. We've had some pretty significant floods. But the context here is different. We're designing a disconnected system. The purpose is to work 95% of the time. It doesn't need to work 100% of the time. If the ground is already saturated and there is saturation excess runoff, what I ask the question back to you, what is the point of having infiltration? What are we trying to mitigate? The answer is nothing. We are trying to mitigate the impacts of urbanisation, 90% of the time when there isn't saturation excess, and where we want to stop the very frequent runoff events from being conveyed directly to creeks. Thank you, Nathan.
Thank you, Mark. Darren, we've had a question come in from Daniel. Good afternoon to you. Saying, great presentation. Darren, can you please also compare the useful life and maintenance of storm bricks with a traditional gravel trench? Thank you, Daniel.
Thanks, Daniel. Just with the useful life, with our storm bricks products, we've got two systems. One's got a design life of 50 years and the other 60 years. How we arrive at those design lives, obviously these products haven't been around that long, but through our creep testing, through the UK standard that prescribes how to test for creep, you can get a graph on how the plastic is deflecting over time. And then what you can do is extrapolate so if you do a test of creep, so you load the cells up for, say, 10,000 hours, then you can extrapolate out to 50 years. The more testing you do, then you can extrapolate more. So what we've done is we've tested some of our products using the creep test to get the useful life based on the calculations from the UK standard. So that's how we arrive at 50 years and 60 years for our product. Obviously, that's based on the limitations of the testing. Our product is made from polypropylene. It's lasts a long time. It's very strong, so there's no. We believe it can last a lot longer than the ones that we market in our brochures. The second question in regards to maintenance of storm bricks, we discussed a lot and shown a lot in our presentation on how the storm bricks is maintained. It's very simple, easily. We designed a product that learned the lessons from the past, that we can get access to it, we can clean it out, we can get around the pillars, we can move to all corners of the storm bricks tank and inspect to see what kind of silt or sediment is inside the tank, and then we can pump it all out. In comparison to a gravel trench, absorption trench, or you have the water going in, but you really don't have any inspection. You just hope that the water and all the sediment filters through. But obviously, over time, in between the pores of the gravel, you might start filling up with sediment and silt, but you really can't get in there. So with absorption trenches, there probably is a limited life, but how long that is really dependent on what's going into your absorption trench. And if you don't clean it before it, then it'll be silt up quicker. But if you have a cleaning product before it that takes out and you maintain that in regular frequencies, then your absorption trench will last a lot longer too.
Thanks, Darren. Back to you, Mark. A question that's come in from Andrew. Andrew's question to you, Mark, is, in my location being North Inland New South Wales, the soils are nearly always black reactive clays with low permeability. Also, any infiltration systems can't be near buildings. What options are there for these conditions? Thanks, Mark.
Thank you, Andrew. Great question. Look, I think for those scenarios, you've absolutely identified the limitations correctly. Reactive soils, for me, is a showstopper for infiltration. Reactive soils also have a tendency to fall apart. You probably know that. They're dispersible. They just don't hold together. The low permeability is another showstopper. If the trench or system, whatever you want to call it, is going to remain full of water, it's quite pointless. What I would be doing in a situation like that is I would be looking to line the storage, and I would be using it as a stormwater harvesting tank, and I would then be looking at disposing of that water by irrigation or perhaps toilet flushing, some other use, some other way of disposing of that water. Thank you. Good question.
Thanks. Thank you for that, Mark. We have a question that's come in from Jonathan, asking you, Darren, what is the design life of ACO cells and what is the maximum load carrying capacity? Thanks, Darren.
I answered the design life question just earlier. So what I'll talk about is the maximum load carrying capacity. With the Stormbrix products, it's undergone a lot of testing, and it was all the testing was based on the UK standard in regards to vertical load testing and lateral testing. And what we've done is we've actually built a structural program that you can get on and use yourself to determine based on what your application is and what kind of live loads you're going to have going over the tank. You can put that into the program. You also can put your pavement type, whether it's a concrete pavement or asphalt pavement or just a landscaped area, and also you can put in what kind of soils it's going to be installed in. And through that structural calculation, we're using the test loads that we've got for our product, and then there's calculations to the UK standard, to the Syria standard, to determine if the product can resist those kind of loads, and even go down to what kind of deflections the tank will have. So if there's going to be a lot of deflection, then you might need to change some of the parameters or design, put a concrete pavement on top, which would distribute the load a bit more. So there is different ways to help design your tank. But in regards to the maximum load carrying capacity, you'll see in our program that you can have heavy rigid vehicles up to 30 tons on it on a industrial slab go over this. So this product's been installed in industrial slabs in warehouses and loading docks under the pavement.
Thank you, Darren. And just staying with you for this final question from Peter, asking, can these be installed under residential dwelling slabs? And what is expected of their performance in clay soils? Thanks, Darren.
Yeah, we don't recommend the Stormbrix system to be installed under a residential slab. Just the dead loads are just a bit too much for it. But in some different commercial buildings, there might be footings or piers or piles that go deep into the foundation. If that's the case, and there's no loads bearing onto the Stormbrix tank vertically, because the slab's being held up by piers and columns, then yes, you can install it under some buildings. But yeah, you've got to make sure that there is no forces from the building slab directly onto the tank. It's not the function of the tank to hold up the building. It's more the function of the ground and or the piers and piles. So yeah, we don't recommend it to be installed under residential dwellings. And yeah, it can be, and also with clay soils, yes, it can be installed in clay soils. It'll be a tank that's wrapped in geomembrane, so it's not an infiltration tank where you'll pipe the water out or reuse it or detain it and release it at a slower rate from the site.
Thanks, Darren. Thank you for that. Today, we've covered a lot: underground stormwater storage for detention or reuse. So let's have a look through the polling results up on the screen. Darren and Mark, can you provide any comments on these results? We had three questions. Yeah.
Yeah, thanks for participating in the poll. Yeah, with these questions, it's more for us, for ACO, to have a look at, I suppose, where we can help in supporting designers with what kind of what kind of services we can provide based on what you design for. Yeah, with this question, it's more that's most of the time when we use the Stormbricks tanks, it is designed for AESTs. I suppose infiltration tanks are used more in coastal areas and in the west in Perth, where there's sandy soils, and with water conservation now, there is a lot of increase, I suppose, in retention for reuse, but there are also a lot of tanks combining retention and detention these days. I've seen designers use both. All they do is use the same tank and just put the pipe out above, maybe halfway up the tank. So anything below the pipe will become retention for reuse, and they'll be connected to a pump. And then anything above that would be detention. And this is a question more for us to understand what the designers need, engineers need from a manufacturer. So, what we want to do is help that way, either through our technical support, through the staff we have here at ACO, or we start creating more and more online do-it-yourself programs. So then you can have access to it, whenever you want. I know that all designers work all different times of the day. So with these online programs, there's always access to them 24/7.
Mark, do you want to comment at all on those results? And thank you for everyone for participating in the poll.
Look, just interesting for me to see that the tanks are mostly used for on-site detention and less so for infiltration and reuse, but really good to see that they're still reused in those applications. Yeah, well done, everybody.
Thank you. Thank you. And this afternoon's session has just whizzed by, and it is all we have time for today. So please join me once again in thanking Mark Liebman and Darren Chan for their time and input. I'd also like to thank Engineers Australia's industry partner ACO for their ongoing support. As always, we're looking to improve and plan for future events. So if you could please complete a short feedback form, which is linked in the description box below. Thank you again for joining us, and we look forward to seeing you at our next Thought Leaders event. Thank you and good afternoon.